Population dynamics involve the study of the population, which may be either semmelporous or heteroporous. Semmelporous populations often have a single reproductive cycle that results in a large number of offspring. When there is only one reproductive cycle, the children all have the same age and lack an age structure. Such populations can be found in insects as well as in annual crops such as rice. Heteroporous populations, on the other hand, have multiple reproductive cycles but only a small number of offspring. Because only a few offspring are born at a time, the individuals have varying ages and can thus be represented using age structures. Human populations, like those in the Philippines, are examples of heteroparity.
Another key to the study of population dynamics is understanding how demographic factors, which are characteristic of a population, influence population size. These demographic factors are namely natality or birth, which is the increase in population through reproduction; mortality or death, which is the decrease in population due to loss caused by natural disasters or accidental events; immigration, which is the one-way inward movement of individuals; and emigration, which is the one-way outward movement of individuals in a population. All four of these factors contribute to either population growth or decline. To be more specific, birth and immigration add new people, increasing the population size, whereas death and emigration are means for individuals to live, decreasing the population size. When birth and immigration rates are greater than death and emigration, this results in a positive population growth, whereas the prominence of death and emigration over the other factors leads to negative growth.
These factors are not mutually exclusive. In fact, ecologists associate these factors with life tables, survivorship curves, and age structures to visualize and predict if a population will grow or shrink. Life tables summarize birth and death rates for organisms at various life stages. It usually represents data for a cohort, but can also be produced using age structure data. Survivorship curves show the proportion of individuals surviving at each age in a given population. It has three general types. This relatively flat curve in type 1 represents low juvenile mortality, as humans and other large mammals invest much time and energy in caring for their young. The type 2 survivorship curve shows more or less constant mortality rates across ages such as birds. The type 3 curve, exhibited by many insects and shellfish, shows high mortality rates for the young but flattens out as individuals who reach maturity survive longer. An age-sex structure is a snapshot of a population in time that shows how its members are distributed across age and sex categories, commonly depicted as a population pyramid. It forms shapes illustrating slow, stable, shrinking, or rapid growth. Slow population growth has an age-sex structure with a pyramid shape, meaning that there are fewer young and reproductive age individuals and more older people, such as in the US. Stable population growth is dome-shaped with a higher proportion of middle-aged and older people than slow age-sex structures. An example is Italy, where there is zero population growth. Some countries have shrinking populations, like Japan. Because young people constitute a small proportion of the population, these population pyramids often pinch inward towards the bottom. Meanwhile, rapid population growth has a sharp pyramid shape in their age structure diagrams. That is, they have a large proportion of younger people, many of whom are or will soon be of reproductive age.
The Philippine population is experiencing such growth. As of 2016, the Philippines has a natural increase in the population of 1,724,603 people per year. As it exhibits heteroparity, the ecological periods are divided into pre-reproductive from 0 to 14 years old, post-reproductive from those over 49 years old, and reproductive from 15 to 49 years old, which indicates that women under this demographic are the ones contributing to the growing population in the country.
Additionally, ecologists see the idea of population growth through mathematical models, where the information gathered is math-based, giving a clear and concise direction to develop accurate assumptions. population growth can be depicted through the exponential growth model and the logistic growth model. The first population growth model is characterized by the absence of factors that limits population growth. The key point of this model is that in an unlimited environment, the population growth rate increases as the population gets larger, yielding a J-shaped growth curve. Meanwhile, the second growth model exhibits the condition of a limited environment, which, unlike the exponential growth model, mirrors the real world wherein the environment has finite resources. According to the logistic growth model, exponential growth can only occur at the beginning when the population size is small and the resources are in abundance. However, as population size gets larger and resources start to deplete, the population growth slows down and eventually stops. Once the growth rate levels off, the model will yield an S-shaped growth curve. An S-shaped growth curve results as the population reaches the maximum size an environment can sustain. This is known as the carrying capacity. There are different factors that determine carrying capacity depending on the individual needs of different organisms, and the limited amount of these resources leads to intraspecific competition. These factors are called environmental resistance factors.
Environmental resistance factors are divided into two main classifications: density dependent factors, which are mainly biotic, and density independent factors, which are abiotic. Under density dependent factors are disease, parasitism, predation, competition, and waste accumulation. These limit population growth by affecting the organism's reproduction and survival. Density-dependent factors decrease the population growth rate as the population increases. Disease and parasitism thrive in the larger population as it is easier for the infection to spread. It is also the case for waste accumulation as waste products accumulate faster in larger populations. Predation increases the prey's death rate while increasing the predator's numbers, which may cause natural cyclical changes in the population. Lastly, competition leads to the depletion of resources that the members of the population need for sustainability. Meanwhile, density-independent factors are factors that affect the population growth rate regardless of the population size, which includes temperature, weather, light intensity, pollutants, and natural disasters. The changes they make in the population growth rate are often abrupt and erratic. For instance, in the case of natural disasters, dying does not depend on the number of individuals in the population. Additionally, the limiting factor may not directly be the cause of death, but rather its consequences, such as loss of habitat and food source.
Recognizing these environmental resistance factors or limiting factors within every ecosystem, such as the availability of food or the effects of predation and disease, prevent a population from becoming too large. Preventing overpopulation is important to ensure the sustainability of the ecosystem, reduction of pollution levels and global warming, protection of habitats, and mitigation of resource depletion issues that point toward population regulation that is much needed for the stability of the planet.